Turenne was a mathematician who was in a labor camp during the Second World War, and he was forced to cart bricks along tracks, but there were places where tracks intersected, and at these places, Turenne would have to lift the cart up over the other track, and that was more difficult than pushing a cart of bricks normally would be. And let me tell you, pushing a cart of bricks is no picnic. However, instead of worrying about his imminent demise, he actually did survive the Second World War. He was doing graph theory. Turenne conjectured that the crossing number of Kn is a quarter times the greatest integer less than or equal to n over 2 times the greatest integer less than or equal to n minus 1 over 2 times the greatest integer less than or equal to n minus 2 over 2 times the greatest integer less than or equal to n minus 3 over 2. So if we plug in n equals 5, we get this quantity, which in fact is 1. But this conjecture is something that has not yet been proven. Maybe you can. Suppose we have a planar graph. It separates the plane into regions. We call these regions faces. Let F be the set of faces. Mind you, I'm really referring to a planar drawing of a planar graph. So here we have 1, 2, 3, 4 faces. And if you think this outer face is a bit weird, imagine you have a country on a globe. There's a whale, and there's a sea monster. So the outer face could be just another country. The number of faces is 4. In this case, we also know the number of vertices is 4, and the number of edges. This brings us to quiz 20. How many vertices are in this graph, how many edges are in this graph, and how many faces are in this graph? And the answer is, well, there are clearly 5 vertices. The number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9. And the number of faces is 1, 2, 3, 4, 5, and 6. Note that with this graph we have 2 faces, and note that in each case, if we do the alternating sum, something we've seen time and time again with the Möbius function, inclusion, exclusion, all of this is related in a precise way, we get the number 2. 4 minus 6 plus 4 is 2. 5 minus 9 plus 6 is 2. 4 minus 4 plus 2 is 2. Of course, these graphs are all in one piece. With this graph, you could say we have 3 faces, so we don't have this relationship. We really need our graphs to be connected. A graph is connected if it's in one piece. This brings us to the celebrated formula of Euler, the blind mathematician. If you take the alternating sum of 0-dimensional points, 1-dimensional edges, and 2-dimensional faces for a planar drawing of a connected graph, you will always get the number 2. And let's check this out. Any tree is planar, and there's only one face. There isn't any enclosure. So we have v minus e plus f being whatever v is. So we have v minus e plus f being the number of edges plus 1 minus the number of edges plus 1, or 1 plus 1, which equals 2. So it works in this case. This brings us to quiz 30 pi. Can you make a planar drawing of a connected graph with only one face that is not a tree? Answer yes or no. And the answer is no. Suppose we do have a connected graph and a planar drawing of that graph with only one face. Then, in fact, it is a tree. Of course, we defined a tree as to be directed graphs, but let's ignore the direction of the edges. Here's our proof. Pick any node. Look at its neighbors. We're going to consider that the root. If you were to start walking in the direction of A, you'll never meet up with your other self who takes the road not taken, because for that to happen, you would be forming an enclosure, which would form a country, a face. But we've already got one face. We've got the, say, outer face of Oceania. And this continues. You could apply the same argument to A if you consider not all the directions you could walk in, but all the directions you can walk in except backwards toward the first point we picked. And so if you think about what you wind up with something that looks like a tree. This brings us to a proof of Euler's formula. We'll use induction again. If we only have one face, then by the lemma we have a tree, and we already saw that the formula of vertices minus edges plus faces equals 2. If we have more than one face, then take a face and remove an edge. This brings us to quiz I. Let's do this operation to a graph. We'll remove this edge. Write down the number of vertices, the number of edges, the number of faces, and the number of vertices, the number of edges, and the number of faces. The answer is, we still have 4 vertices, but the number of edges has gone down by 1, and the number of faces has gone down by 1. The graph is still connected because you could still go around and get everywhere you needed to get to, just not by that shortcut. And of course, it's still a planar drawing. We don't increase the number of crossings by removing edges. So, by the induction hypothesis, the number of vertices minus the number of edges, which is the number of original edges minus 1, plus the number of faces, which is the number of original faces minus 1, equals 2. But of course, this is just v minus e plus f equaling 2. So that's an inequality. That's an equation relating the number of vertices, edges, and faces. Now let's look at some inequalities, because that tells us what planar graphs must have. But if you don't have a planar graph to begin with, there are no faces. So we need to know how we can talk about faces when there aren't any. So we're going to derive some inequalities involving just the number of vertices and edges for planar graphs. If we have at least 2 edges, then 3 times the number of faces is less than or equal to 2 times the number of edges. And if the graph has no triangles, then 4 times the number of faces is less than or equal to 2 times the number of edges. How do we prove this? Each face has at least 3 edges. They look like this, or like this, and so on. But you don't have a face without having at least 3 edges. However, countries neighbor each other, so we can't just say that the number of edges is 3 times the number of countries, because we're counting edges twice. So 3 times the number of faces divided by 2 is going to be bounded above by the number of edges. Let's look here. We have 3 faces and 6 edges. And sure enough, 3 times 3 is less than or equal to 2 times 6. Now, if the graph has no triangles, then that means there are no 3-sided faces. If the graph has no 3-sided faces, we could use the number 4 where we used 3. Now, what's this issue here with the number of edges being at least 2? Well, if there's only 1 edge, then we really only have a strange kind of country, and that's the whole issue there. We want to have a country which looks like what we'd expect. But if we have at least 2 edges and only 1 face, we still have a tree, and if we have at least 2 edges, then we would have 3 less than or equal to 4. So that deals with that situation where we only have 1 face. Let's look at an example. We have 4 vertices, 5 edges, and 3 faces. We do clearly have some triangles. 3 times 3 is less than or equal to 2 times 5, which is 10. Here we have no triangles. 4 vertices, 4 edges, 2 faces, and 6 is less than or equal to 8. We get as a corollary of that proposition that the number of edges is less than or equal to 3 times the number of vertices minus 6, and this is what we're aiming toward. We want relationships between the number of edges and vertices for a planar graph, so we don't have to talk about faces. But what's even better is that we don't need to assume the graph is connected. If the graph is disconnected and we have a planar drawing, it's clear that we can add edges to make the graph connected. And if we get this inequality when we've added edges, we have the inequality even before. This is a nifty proof. We have Euler's theorem, and we have arithmetic, and we have the previous result that says 3 times the number of faces is less than or equal to 2 times the number of edges. Voila! So confirm the previous result for this graph. Write a number here and a number there. And the answer is, since there are 4 vertices and 5 edges, and 3 times 4 minus 6 is 6, we're just confirming that 5 is less than or equal to 6. Let deg v be the degree of vertex v. Someone with a lot of friends has high degree, and in the analysis of terrorist cells, such a node is considered important. This brings us to quiz 1000 to the power e. For these graphs, write down the degrees of the vertices. And the answer is, this vertex has degree 2, as does this has degree 3, as does this, and each vertex here has degree 4.